Hello and welcome everyone. In previously you all know about the physical units and the dimension analysis. Today we are going to learn about the application and limitation of dimension analysis. Now before doing that, let us do a brief recall on dimension analysis. Like what is the dimensional equation is. Now the equation obtained when we equal a physical quantity with its dimensional formula are called dimensional equations. For example, F is equal to ml to the power minus 2. It is the dimensional equation of force. Now, there are two important rules that we should recollect first before go beyond. The first one is the unit in which the quantities are to be expressed do not affect the dimension of the quantity. Like an area is still going to be an area whether it is represented in terms of meter square or centimeter square. Therefore, its dimension will not be changed. It will be same, that is L square. Now for the second rule, which is the principle of homogeneity, the dimension of the left hand side and the right hand side of a correct physical relation must be same. For example, if we have a physical relation whose left hand side dimension represents the velocity dimension, then its right hand side has to be the dimension of velocity. Otherwise, it will be not physically correct equation. There are some aspect to it, like if we have a physical relation where x is equal to y plus z, then the dimension of x must be equal to the dimension of y and the dimension of z. But if we have a physical relation where x is equal to y and z, then the dimension of x must be equal to the product of y and z, and this will be same for the division rule. Now for the first application, to find the unit of a physical quantity in a given system of units. Let us have an example. Here we need to find the unit of force in SI unit systems. Now from equation 1 we know that F is equal to ml to the power minus 2. Note that here we always represent the dimension in terms of fundamental quantities like m, l and t. Therefore the SI unit of m, l and t are kg for mass, meter for length and second for t. These are all represented in terms of SI unit system. Therefore the SI unit of force is kg meter per second square. Now for the next application, to convert a physical quantity from one unit system to other unit system. Let us take an example where we are going to convert from SI unit system to CGS or vice versa. Let us have a physical quantity where the value in SI is N1 and the value in CGS is N2. Now the value means like 1.2, 1, 2, etc. Let their units in a corresponding unit system are U1 and U2. The unit means like meter, joule, kg in SI system and centimeter, gram, arc in CGS system. And the dimensions are like this. Now to convert from SI to CGS, we use this formula, and to convert from CGS to SI, we use this formula. Note that the notations here for SI to CGS represent the value of and the unit in SI, and the notation M1, L1 and T1 are the values of mass, length and time in SI system. Similarly in here the notation is just reverse of the previous one. Let us name it the equation 2. Let us have an example. Now in this example we need to find how much it is of 5 Newton. That is 5 Newton is equal to how much time. Now here Newton is the unit of force in SI system. So we are going to convert from SI to CGS system. Therefore we are going to use the equation 2 for this conversation. Therefore 5 Newton is equal to 5 into 1 kg by 1 gram. 1 meter per 1 centimeter, 1 second per 1 second whole to the power minus 2 dyne. This we can obtain from equation 2. Now we can represent the kg and meter in terms of its corresponding gram and centimeter. Therefore we can have this thing. Here we can eliminate grams, centimeter and second, and we can multiply 1000 to 100, and we can find finally the 5 Newton is equal to 5 into 10 to the power 5 time. Now for the third example, a third application, checking the correctness of the dimensional equation. Let us take an example. Here we have two relations relating the displacement s with velocity v and time t. Now which one of these is correct? To do that, let us check their dimensions of both sides. Therefore, the left hand side dimension for both of these equations will be L, and the right hand side dimension for these two equations will be as follows. If we calculate the power, we can find the left hand side equation for the first one is equals to the left hand side equation right hand side equation of the first equation. Here we are going to just checking for the dimensional correctness. Therefore from the first equation we can find out that L is equal to L. So this first equation is just according with the principle of homogeneity. So according to the principle of homogeneity we can write the first one is correct and the second one is wrong, because the left hand side dimension is equals to the right hand side dimension for the first one, but for the next one it is not. Let us do another example. Here it is given that in an experiment the mass and velocity v and c and mass m and m0 are related by these three equations. Now which one of them is correct? To do that we will use the previous knowledge again. We will first check the left hand side dimension, which is m for all of them, because mass has the dimension of m. Now if we are going to check the dimensional correctness for the first equation, we can check its right hand side. The right hand side represented by this. Now m0 is also a mass, so its dimension will be m, and v and c both are velocity, so their dimension will be this. If we calculate them, we can find from the first equation we have this one. So here we can see that left hand side is not equal to the right hand side, so it is not uh, it is just violating the principle of homogeneity, therefore it is wrong. We can do the same for the second equation, and we can find that it is also not correct, because it is also violating the principle of homogeneity. If we do the same for the third equation, we can find this. Here we can see that the left hand side dimension is equals to the right hand side dimension, so therefore according to the principle of homogeneity we can say this third one is correct. For the final application, we can use dimensional analysis as a tool to derive new physical relations. Let's take an example. Your friend told you that the time period of a simple pendulum might be depends on the length of the pendulum, mass of the pendulum, and the gravitational acceleration. Let us write it in terms of mathematical equation, which is this one. T is proportional to L to the power alpha, G to the power beta, and M to the power gamma. If we find the value of alpha, beta, gamma from here, we can derive our desirable equation. Now this is the pendulum, where L represents the length of the wire and M is the mass of the bob. Now we can represent this equation in terms of their dimensional equation. We can substitute the proportionality sign by a proportionality constant. Now don't worry about the k, because it is a dimensional constant, so in our dimensional analysis it will not affect anything. Now if we equate the power of T, L and M from the both sides, we can find three equations: gamma equal to 0, alpha plus beta equal to 0, and minus 2b is equal to 1. From this we can find the value of alpha, beta, gamma is as follows. By substituting these values to our previous equation, we can find T is equal to K root over L by G. So this is our final relation. So we can derive a new relation just from a given argument. But not only that, we can also prove the dependency of certain physical quantities on our equation. Like here, it says that it does not depend on mass. Okay, let's see the limitation of dimensional analysis. For the first limitation, it does not distinguish between the physical quantities having the same dimension. For example, momentum and impulse and energy and torque. Momentum and impulse have the same dimension and energy and torque has the same dimension. So it cannot be distinguished by using the dimensional analysis method. For the second limitation, the method of dimension can only test the dimensional validity but not the exact relationship between the physical quantities. For example, relative velocity can be represented by these two equations. They both are dimensionally correct, but the first one is physically correct and the second one is not. So we can do another example, like the focal length of a lens can be represented by these two equations. They both are dimensionally correct, but the first one is physically incorrect and the second one is physically correct. Okay, let us see the third limitation. The exact value of the dimensional constant cannot be measured by this method. As we have seen before that T is equal to K root over L by G, we cannot find the value of K by using the dimensional analysis. Although we can find the value of K by using some different method like graphical analysis or experimental method, and the value of K is basically 2 pi. The fourth limitation is that the dimensional analysis cannot give us the angular dependency of a physical equation. For example, in a simple harmonic motion, the displacement can be represented as this. We cannot find the sine omega t by dimensional analysis because it is a dimensionless term. We can write its dimension as this. Okay. Now this is also true for other functions like trigonometric functions, exponential functions, and logarithmic functions. For the fifth and final limitation, we cannot derive any relations which includes summations or subtraction by this method. Like here are two important relations we know, the famous relations. Here see that for the first equation there is a subtraction sign and for the second equation there is a summation sign. These two equations cannot be derived by using the application 4 or the dimensional analysis method. Okay.